I just heard a beep. May I know who just joined?
Hi Rajesh, this is Partha here.
Yeah, hi Partha. So SVC, as we know, is just a SAN volume controller rebranded as Spectrum Virtualized. We will be covering SVC and StoreWise V7000. For many of the features are pretty much the same. There is not going to be too much of a distinction placed on the emphasis of this. And also, this session will not be covering how we will be doing firmware updates or the internal zoning of the SVC clusters. So that will be covered in the sense as what is required only from a migration perspective. So at that time, you definitely need to know what are the zonings required for inter-node communication as well as metro mirror and global mirror and other such requirements. But apart from that, the initial sessions will be handled by Rajesh Vijay Prakash, who has worked extensively on SVC and DS8K. And we also have Praveen, who worked with EMC and is now having a lot of knowledge on SVC. I'll give it to them. Please continue. So hello everybody, how are you? So as Raj already told you guys that during this training session we are going to cover SVC and StoreWise V7000 both. And both of these products have many similarities, and that's the reason we thought of covering both of these products in this session, in this training program. There are certain dissimilarities that we definitely have and we are definitely going to discuss those things as well during our training program. Okay? So without wasting time, I think let us start with the agenda of this training program. So following is the agenda of this training program. We will start with SVC StoreWise V7000 hardware architecture. Then we will go ahead with SVC storage provisioning. We will go ahead with SVC host access, where we'll be discussing, how to connect host and, how to provide that provisioning to the host that are connected to SVC or StoreWise V7000. We will be discussing about Spectrum Virtualized advanced features, then thin provisioning and volume mirroring, Spectrum Virtualized data migration. That is one of the most important topics that we need to discuss because that is part of our day-to-day job, right? And we will be discussing about Spectrum Virtualized copy services, which will include flash copy, global mirror, macro mirror, etc., and user access and roles. So let us start with SVC hardware architecture initially, and let us try to understand where exactly a Spectrum Virtualized falls in our complete architecture. So as you can see in this, we can clearly see in this picture, there are three layers that we see here, okay? So we see backend storage subsystem, that is one layer. Then we have the Spectrum Virtualized layer, that is the middle layer, and on the top we do see host that can be connected to SVC, okay? So we can clearly see three layers here. So what we do here is, as we see that we have backend storage subsystems, we provide storage space from backend storage subsystems to SVC. One point of importance is, when we are actually discussing SVC, it is assumed that you are already aware of storage virtualization. All the storage virtualization can happen at three levels, either at the host level or at the network level. By network level, we mean either through SAN routers or storage controllers, or at the disk level. Spectrum Virtualized, or SVC as we call it, does this at the storage controller level, leveraging the storage area network. And as such, all the discussions that we are going to do will essentially leverage this functionality of virtualization. I request all of you to go through the storage virtualization features or the basics once again, if the topics are not readily appreciated by your head, just in case you have lost it for the time. Okay, so as you see here that we have storage subsystems at the back end, and which can be either IBM, EMC, HP, or any other storage subsystem. So storage space from the backend storage subsystem is given to SVC. SVC creates an extra virtualization layer on top of the backend storage subsystem and present that space to the host. Okay, how is it done? We are going to discuss in upcoming classes about that. Okay, but this is this is the basic knowledge that we need to have in order to understand the further classes that we are going to discuss. Okay, so we can see the total 8 nodes here. So we can see two set of nodes. functionality of handling a specific volume or set of volumes. Okay. So whatever I/O activity we have on that volume is processed through the I/O group that we have over here. Okay. So now let us start discussing about the individual nodes, how they look like.
Okay. So for you guys, like what is SVC? Just I want to know you guys to what extent you know what SVC is.
Another controller.
You have storage as a controller?
SVC is another controller.
It's only a controller? So what it is actually? What it plays a role in a storage?
It's like a memory bank has a bunch of disk, like a bunch of storage.
Okay.
So we can manage like data transfer, data migration, data copy. So we have a lot of features to do this by using of the SVC. So we can do three kinds of migration.
Okay.
Coming back, when I say it's a controller.
So for you guys to know, SVC is a logical device which sits in between the storage and the host, which acts for the virtualization. So you don't get things like the storage. It's a storage. It's a gateway. So it manages the backend storages. So then the I/O group, as we discussed, you guys know what I/O group is. I/O group,
In essence, just a cluster.
it's a cluster. It's a two node acts as a single I/O path. So cluster group and acts as a single I/O path. It's a hardware. Two nodes means when I say two nodes, it's a one server. You can take it as a server when you have the Windows background or something like you can take it as one server. Two nodes act as a one cluster. It's called as I/O group.
Let's put it this way. SVC is implemented as a cluster appliance in the storage network layer. So it is hardware because there are physically two nodes present, but they work as a single cluster. And it is an appliance, but essentially all it does is leverage the storage virtualization that I've mentioned in the SAN network layer.
So it also provides us a single management GUI. You know, no matter whatever backend storage subsystem. Yeah.
Both nodes act as a single processing unit.
So it provides some kind of ease of management also because we have a single GUI using which we can, manage multiple storages at the back end.
Technically, you mean to say like whatever be the storage boxes connected to SVC, one GUI is enough to take care of all.
Yeah, that is one of the features you can say. We'll come to that in the later slides. So we can have minimum one I/O group, but we can extend it up to 4 I/O groups as per the requirement that we have. It depends on that. 4 I/O group means total 8 nodes basically. So let us look at the node part. Okay, prior to that, let us discuss about different models of SVC. So we have SVC CG8 model, and that is a little older model that we had. The latest model that we have is SVC DH8, and we also have SVC 24F expansion enclosure. So basically, this expansion enclosure is utilized to have the internal storage in SVC. Apart from taking space from the external storage subsystems, we also have a facility in SVC where we can have internal storages assigned to it, and we can allocate space using that as well.
Just a point to add, these are not the only SVC models available. SVC is currently in its 8th generation. So there are quite a few older generation models which we might not be covering here, but essentially the functionality remains the same. But the latest models acquiring a little more in the form of compression or more memory, etc. We will come to those points as we are progressing through the slides.
So the old CCI is the one which previous model which does not have internal storage to present to the host. But there is a new model which will come up DH8 as a storage which can be. That's the reason where we have an expansion enclosure.
So we can add
expansion enclosure doesn't operate the I/O operations or something directly from the this thing. It's an expansion to the existing nodes.
So apart from having external storage, we also have internal storage in case of a DH8. So we can provide space from that internal storage as well.
IBM. These are it's the IBM proprietary, no competitor till 2003. There is no, even EMC uses SVC for the migration. They have different tools, but even EMC hires the SVC for the migration. Because there's a reason when you say go back to the back slide. What is the advantage when it comes to the SVC? Let's say you see back-end storage, subsystem, whatever, we can support these many components to back-end. Let it be an Hitachi, NetApp, EMC, whatever it is. So back-end, the front-end, it remains the same. So to the host. So the migration process is very easy, and online we can go to the migration for this.
Since we are already in the migration team, most of us, let me explain that point a little further. When we are referring as migration in this session, it is mostly storage migration and not an end-to-end data center or a host migration. Because most of the host migrations, as you know, might require some downtime. But when you are migrating only storage, utilizing SVC in the SAN network layer, a storage can be migrated from an existing storage device to a brand new one without involving any downtime, as long as they are virtualized behind an SVC. That's the point behind an online migration, and all the migration that we refer to in these training sessions refers to only storage level migration and not a complete migration.
And we can also see in this picture, right, we can have different storage subsystems here. So you can connect one or more storage subsystems at the back end, and you can perform a migration. How do we do that? We are going to cover it in upcoming classes. Okay? So let us start with the hardware architecture. So this is CG8 model, okay, SVC CG8 model. This is the front panel of SVC CG8, where we can clearly see the node cluster LED. We can see the panels. Using this panel, we can actually configure the IP address, management IP address of the complete cluster, and we can also configure service assistant IP address that can be used for troubleshooting purpose as well. Okay, and apart from it, we have 5-button keyboard here. Using this navigation panel, we can navigate through different options that we see at the front panel. Okay, this is how it is. And you have operator information panel where you have power on-off button, and you can also see the Wi-Fi network connectivity and other, in case if there is some fault in the node, it will be available. You can clearly see it from the operator information panel itself. Okay. So apart from having this, it also has a dual battery backup power supply for battery backup purpose. In case if commercial power supply goes down, you always have a battery backup power supply for backing it up for some period of time. So why we need the battery backup power supply? We are going to discuss it in upcoming classes. There is a specific purpose of it. Okay. So let us go to the next slide now. So now this is the rear end of CG8 model. This is how it looks like. I think this is one of the most important parts we should be concentrating on, because this part tells us about the front-end connectivity, back-end connectivity, or inter-node communication that happens between different nodes and different IO groups. So we can clearly see here there are 4 ports, right? We can clearly see 4 ports here that are used for fiber channel connectivity, and they support 2, 4, and 8 Gbps fiber channel connectivity. Okay, these 4 ports. Apart from having this 4 ports for fiber channel connectivity, we also have iSCSI port for supporting 10 Gbps speed. Okay, 10 Gbps iSCSI connectivity. So for that purpose, we have these 2 ports. We are talking about individual node here. So when we talk about complete IO group, we just double these number of counts. Okay, and we also have 2 separate Ethernet ports, E1 and E2 ports. Out of this E1 port can be used for management purpose. Okay, management IP is configured on this E1 port. Then we also have E2 port, which can be used for 1 Gbps iSCSI connectivity. But overall, we can utilize both of these ports for 1 Gbps iSCSI connectivity as well, in case if you want to use them for management connectivity as well as 1 Gbps iSCSI connectivity. So you can use a VLAN configuration for that purpose. Correct? So this is how it looks like, and we have 2 power supplies. Basically, this is where we connect the main power supply, which is coming. And as I told you before, we do have battery backup supply for some other purpose that you can see at the front end itself. Okay. So now let us look closely at the feature that I described before on the previous slide. So it uses one quad-core processor with 24 GB memory. Okay. So all kind of processing activities on that node are handled by this quad-core processor. The memory is 24 GB memory. Then as I discussed before, that it supports up to 4 optional. I've not discussed about this, but it has an option of adding 4 SSD drives inside it. So once you open the front panel, you will be able to clearly see 4 SSD drives per node. Okay, not a front panel. Once you read your book, as a normal server, we need to open it. There inside it will be there. So that was a disadvantage where we had it's not a hot swappable or something for the SVC in the previous version. The newer version has hot swappable everything. In next picture, we will be able to see. So per node supports, one individual node supports 4 drives, complete IO group supports 8 drives, and once we talk about the fully configured system, it supports up to 32 internal drives. So those 32 internal drives can also be utilized for internal storage, where we provide the internal storage to SVC and we can configure that as well. We can create pools, we can create volumes using that. Okay, and we have, as we could see in the previous picture, we use one 4-port 8 Gbps fiber channel adapter that is on board, of course, that we saw, and we have one 2-port 10 Gbps FCOE converged network adapter that is used for fiber channel over Ethernet connectivity, right? So it provides us iSCSI as well as FCOE connectivity. We can utilize that for that purpose. And we, as I said before, FCOE host attachment we can do, and iSCSI host attachment is also there. That is 1 GB Ethernet and optional 10 GB Ethernet. Okay, so I was telling you about the 2 ports, right? Even E2 ports in the previous picture. So those ports can be utilized for management connectivity purpose as well as 1 Gbps iSCSI connectivity as well. Okay, and dual redundant power supply. It also supports optional IBM real-time compression. So that is one of the beautiful features of SVC, in which we can compress the volumes so that for the space optimization purpose. So it does the real-time compression. In other like EMC and other technologies, you might have heard about volume compression, but there the compression is not the real-time compression. The compression is done at the disk drive level. Here, the compression is done at the cache level. Okay, so before the data is written to the actual disk drive, we perform the compression. So that kind of compression we are using here. So that compression is much more better than the compression that we are using in other storage.
It is better in the sense that you essentially leverage time. So you don't have to send the data already to the disk drive and then perform compression as a separate option or as a separate operation. Even when the data resides in the cache, the volume will get a compressed data directly, thereby removing the necessity to utilize valuable CPU cycles as a separate operation. Essentially, it frees up the CPU, and it also frees up the time that is required to first of all write the data to the disk drives one time, and then perform a separate compression. That's the advantage of the real-time compression. How that is achieved and what is the hardware required for it, we will see in the forthcoming slides.
So this is the hardware which we required in the newer version. In this version, we had a lagging of the IOPS, everything with the things. To address that, we had a new version which has come up with the aggregated code, everything for this.
So yeah, that's for both the write and read in the cache. That's compression.
No, only for the write. Compression will be done only for the write.
That's the compression for volumes. It's not compression for reading.
And since it uses quad-core processor, and it has 24 GB of memory, at that point of time, compression used to take lots of time. So with the latest model, we have come up with some additional features which we'll be discussing in the upcoming slides. Okay. So this is how it looks like. We were talking about the drives that reside in individual nodes. So as you can see here, we have total for a fully configured system, we can clearly see total 4 IO groups with 2 nodes each, and each node contains 4 drives, and each IO group contains total 8 drives. So we can have up to 32 drives, 32 SSD, solid state drives in case of CGF model. Okay, and these drives, this space can be utilized for space. We can configure space using that. We can create volumes using this space, this drive as well. Okay, for that purpose we are utilizing this. Okay. The So as you can see, each SSD represents as a drive for array creation, hot pluggable and hot swappable. These drives are, and up to 4 SSD per SVC node and up to 32 per cluster. And the RAID configuration that is supported is RAID 0, RAID 1, and RAID 1.0. I hope everybody understands the RAID concept at this time, right? So these kind of RAIDs that are supported in case of this model. Okay. Now let us check the latest model, the DH8 model that we already, in the first slide we were discussing about that. So DH8 model, this is how from the front side DH8 model looks like. So in DH8 model, you can have up to total 8 internal drives. Out of these 8 internal drives, these first two drives are basically used for storing firmware in them. And these are called boot drives. And these boot drives are basically mirror drives where each drive contains firmware and another drive contains a copy of that firmware. Okay, so we have 2 drives for redundancy purpose. So that in case if one drive gets faulted, we always have another drive in order to back it up. Okay. Apart from storing the firmware, this is also used for storing some data. What is that condition? I'll be discussing about that. Okay, in upcoming slides. But it does that. It solves that purpose as well. Apart from these 2 drives, remaining 6 drives are basically, when we look at the document, it says these are for future use. What is it used? We don't know as of now. Okay, so once I know it, I will definitely tell you about that. And we have 2 batteries, basically for battery backup purpose, as I told you before. Now, what is the purpose of the battery backup? We'll be discussing about that as well. Okay, and we can see node status LED, we can see node fault LED, we can see battery status LED at the front end. Apart from this, we can see operator information panel, which can tell us about what is the IP address that is configured, and it will show us that IP address as well. Okay, and there are 2 USB ports, though these are not also currently used. Okay, and we have a VGA connector where we can connect the monitor. Okay. Now let us look at the rear end of DH8 model. This is also one of the most important parts we should be aware of, because from here we provide inter-node connectivity, inter-IO group connectivity, we provide front-end connectivity to the hosts or the servers, and we provide back-end connectivity to the storage subsystems that gets connected to SVC, right? So in the first picture where we could see the complete architecture, we saw different layers. We saw storage subsystems, we saw hosts, right? And we saw different nodes, and we also saw IO groups. So that connectivity is provided by all of these ports. So we'll be discussing about individual host interface cards, because we have to connect individual host interface cards here. But let us have a look at the things that we can see here. Okay, so we can clearly see 1, 2, 3 ports here. So these ports can be utilized for 1 Gbps iSCSI connectivity. Okay, apart from using them for 1 Gbps iSCSI connectivity, port number 1 and port number 2 can also be utilized for providing the management access. So either you can have a single IP configured as a management IP, or you can have 2 IPs configured as management IPs. So it's as per your choice. But in case if one node goes down, automatically that IP which you configured for this port gets transferred to another node. Okay, there are similar 3 ports available at another node as well. So if in case if this node goes down, automatically that IP will get transferred to another node. Same the cluster concept. To the other node of the same IO group. Same IO. So that we have to get. Okay. Now you can see one port that is called technician port. This is the 4th port. This port is basically used for initialization of SVC. So during the initialization phase, when we don't have an IP configured to these ports, because in the initial stage when you get the new SVC, you won't have any IP configured. So you need to connect the system to this technician port, and you need to configure everything. This is where you configure everything. And this port is not being used currently. And then again, we have a VGA port for connecting monitor. We have a serial port for troubleshooting purpose. And we have 2 power supplies and 4 USB ports. Again, these ports are not currently in use as per the material that we got for this. Okay. So this is how it looks like from the rear side. Now let us concentrate on the host interface part. How host interface cards, okay, what kind of connectivity they provide and how they look like.
So these are the places where we can insert the, okay, we have in the next one.
Yeah, we have it. So now let us have a close look at this. Okay. So as we can see here, we can see processor 1 and processor 2. By default, when you buy an SVC, it comes with one processor, processor 1. Okay. What is the second?
For practical purposes, we are only considering the DH8 for all the slides from now. This is not the same structure as that of the other older versions of SVC. Obviously, the hardware structure is different. For the purposes of this transition, we are going with the most modern available option.
Yeah. So by default, when you buy the DH8 model, it will come with a single processor and it will have these slots. By default, it will have the first slot where you will have 4 fiber channel 8 Gbps ports. Okay? You will have a host interface card which will be having 4 ports, 4 fiber channel ports. Now, as per your requirement, you can definitely obviously extend the capability of it. You can have more number of fiber channel ports, you can have more number of I2V ports, you can have more ports for fiber channel over Ethernet connectivity, etc. So what are those ports? So by default, it comes with one card with 4 ports for 8 Gbps connectivity. You can add additional 3 host interface cards to it. So it means you can have total 16 8 Gbps fiber channel ports. Okay, in case of this model. We are just talking about this model as Raj told you. Now, once it comes to 16 Gbps fiber channel connectivity, you can have total 2 host interface cards with 4 ports each. So it means you can have total 8 ports, 16 Gbps, 8 ports. Okay, in that case. Once it comes to I2V connectivity, as I told you before, first 3 ports that we were using for 1 Gbps. Now you can have, for 10 Gbps I2V connectivity, you can have total 2 host interface cards. When I'm talking about this configuration, I'm talking about the maximum capability, maximum number of ports. Now, if you want to have a different permutation and combination where you want to have fiber channel as well as I2V both, then you will have to limit it because we have a limitation in terms of number of host interface cards that we can connect here. Okay? Now, slot, as it says here, slot number 2 and slot number 5 supports an optional 4-port 10 Gbps Ethernet card. So 10 Gbps I2V cards we can connect on slot number 2 and slot number 5. But again, this is not a constraint. I mean, you can connect the card wherever you want as long as those host interface card is free. But as for the way they implement it, they suggest the I2V cards to get connected to slot number 2 and slot number 5. Okay. Then you have slot number 3 that is used for SAS connectivity. So as you might be knowing that we have internal storage in this case, in this model, right, in case of DH8. So we can have maximum up to 2 expansion enclosures. So there should be a way where we should be able to connect this node to the internal storage as well, right? How do we connect it? We connect it using this SAS card. So that SAS card usually we are going to connect at slot number 3 with 2 ports. That card will be having 2 SAS ports with 6 Gbps speed. Okay. So since we can have 2 expansion enclosures, we are having single card with 2 SAS ports here, and in another node also we will do the same configuration. Okay. Now we are done with the fiber channel ports, I2V ports, 1 Gbps, 10 Gbps, 8 Gbps, and 16 Gbps all. Now we will talk about the second processor. Okay. So as we discussed before in the previous slides, that it provides us an option to do a volume compression. So in case of DH8, if you want to do a volume compression, you need to have a compression accelerator card connected to slot number 4 and slot number 6. So you can either have a single card or you need to have 2 cards. But those cards will only be functional if you have another processor connected to it. Because in order to perform that compression, definitely you need some kind of processing capability, right? So in order to do that, we need to have a second processor here. So this second processor will not be utilized if you are using for compression. It will never be utilized for I/O processing. It will be utilized only for volume compression purpose. Okay. Other thing is, see, as in the previous generation, each processor was supporting 32 GB of cache, right? 32 GB here, 32 GB here. But in order to perform volume compression, it will take 4 GB of cache from this processor. So it means for performing volume compression, it will utilize 36 GB of cache. Okay? Fine? So, but in the latest model, I studied somewhere that currently it is supporting up to 64 GB of cache per processor. Okay? So why this compression?
64 GB, it's a totally 128 GB. It comes at 64 GB.
No, actually I read it somewhere that 64 GB per node also it is supporting now, per processor, something like that. That's right.
Per processor or per node?
Per node.
We consider as a per node.
So I think it should be clear now, right? At least this part. So how that compression accelerator card looks like, we are going to see in the upcoming slides. Okay. So now let us look at the processor, how the processor is. Okay, so we are talking about processor here. So processor 1, it is in the previous slide for TGH we saw that we were utilizing quad core processor. Right? Here we are using 8-core CPU with 32 GB memory. Right? And what is it? It's Intel E5 2650 version 2 2.6 GHz Ivy bridge processor and minimum 1 host interface card. So I already told you before that when you buy new SVC, it comes with a single host interface card, right? So you can expand the capability as per your requirements, correct? And second IO host interface card and staff host interface card can be added for support for internal connectivity, right? So similar, architecture-wise, second processor is also similar, but it says required with IO slot 4 and 6 and third host interface card. So basically, slot number 4, first slot in the second processor and the third slot in the second processor is basically utilized for compression accelerator card, which is utilized for compressing the volumes, right? And the middle slot can be utilized for connecting other host interface card. For example, for fiber channel connectivity, for I2C connectivity, etc. Okay? And it uses IBM system 3650 M4 server architecture. That specific architecture it utilizes. Okay? So now, let us have a look at compression accelerator card here. So this is how compression accelerator card looks like. So each node supports up to 2 compression accelerator cards, correct? Installed in slots 4 and 6, as I discussed before, can be installed in any IO slot that is connected to second processor if available. So in case if third slot is available and we want to utilize it to connect compression accelerator card, we can definitely do that. But as a practice, we are using slot number 4 and slot number 6. So most of the time you'll find it like that. And again it says, there is one more condition. Suppose you have a single IO group where you have a single node with compression accelerator card, and you want to add another node. Definitely you will add another node to a single IO group, right? For redundancy purpose and all. So if you try to add another node without compression accelerator card, it will not happen. It will not allow you to do that. In case if you are having compression accelerator card on one node, you are supposed to have compression accelerator card on another node as well. If you don't have it, you will not be able to add it. And there is a technical reason behind it that we will be discussing about. Okay? We'll definitely discuss it. Now, if you are using a single compression accelerator card, it supports up to 200 volumes. Okay. If you want to have 2 compression accelerator cards, it will support up to 512 volumes per node. So you can compress up to 512 volumes per node in case if you are using 2 compression accelerator cards. And if you are using 1 compression accelerator card, you can compress only a single volume. Sorry, you can compress 200 volumes. Correct? So that is the difference. Right? So now we have discussed a lot about expansion, enclosure, and tabs, ports, etc. So let us have a look at the expansion enclosure. How does it look like? So this is the picture of your expansion enclosure 24F. So this expansion enclosures, you can add up to 2 expansion enclosure in case of SVC. Okay, or a single IO group. Okay. So when I talk about 2 expansion enclosures, I am talking about total 48 drives. A single expansion enclosure can have at max up to 24 drives. At max, I am telling. Why? Because you have 2 options here. You can have 3.5 inches drive and you can have 2.5 inches drive. In case if you are using 2.5 inches drive, it will support 24 drives per expansion enclosure. In case if you are using 3.5 inches drive, it will support 12 drives per expansion enclosure. Okay, because in that case, drives will be, will be mounted horizontally in case if you are using, larger drives.
Which is right. So it consumes more space and consumes more space and consumes more space.
And so here it is, and it has dual AC power supply, canister and cooling. Okay, and I/O connectivity is limited to 2 adapters. Okay, we'll be discussing about that, and it has basically it has 12 GB SAS card installed in case of DHA, and slot free. There is a connectivity. We'll be looking at that closely. How SVC nodes are connected to extension enclosures. Okay, there is a connectivity diagram that we'll be able to see how the backend connectivity happens between your SVC and the extension enclosure. Okay. Okay, so now let us look at the rear end of it. So this is how it looks from the rear end. You can have, as I told you before, that we have SAS connectivity. So once we talk about SAS connectivity, we have the SAS ports. So these are the ports where your SAS connectivity happens between your node and the extension enclosure. Okay, one SAS port is this, another SAS port is this, and this another SAS port is not utilized currently. Okay, and then you have power LED and link fault LED here. That is for the port, and then you have LED panel for power status and fault LED. So this is how our rear end of the extension enclosure looks like. In upcoming slide, we have a connectivity diagram which is going to clear these things a little more. So now, this is the backend connectivity diagram where you can clearly see the connectivity between your. This is the diagram where you can see connectivity between your nodes and the extension enclosure. So as you can see in the diagram, these are the SAS ports that we can clearly see, and these are the nodes that we can clearly see. So since we are using 2 nodes per I/O group, we have to make sure that connectivity is provided between those 2 nodes and the extension enclosure, right? We cannot leave one node like that, correct? So how the connectivity happens? So as you can clearly see, this is one extension enclosure, this is another extension enclosure. So one port, as I talked before, that there are 2 SAS ports, right? There are 2 SAS ports here. So one of the SAS ports comes to this enclosure, and another SAS port goes to this enclosure. So it will make sure that this node has connectivity with both the enclosures, correct? In the same fashion, you have another node which provides connectivity between this port and this enclosure, and you have another port which provides connectivity between another node and this enclosure, right? So this is how the connectivity is provided in case of this model, okay, DHF model. I'm sorry? In this model we have, but there are other boxes where we can add additional enclosures. So that is in case of V7000. So we'll be discussing about that.
There is no redundancy, only one way to go.
In two cases, you have redundancy, 1 and 2. Node A, node B. You have 2 redundancies for the same. And these nodes are also. Yeah, and these 2 nodes are also connected with each other, right? So these nodes are not isolated with each other. There is a connectivity between these nodes as well. Yeah. So we have to provide the fiber channel connectivity between nodes as well, as we discussed before. And this is the SVC boot disk. So when we look at the boot disk, basically there are, as I discussed before, there are total 8 drives. Out of these 8 drives, 2 drives are used for booting purpose, and they contain exact copy of the firmware of SVC. And size of the boot drive is 300 GB, and this is 10K SAS drive. And now, here I was talking about, I was discussing about the battery backup. What is the use of the battery backup? Basically, people who are familiar with storage technology, they might be knowing that whatever data we write in the storage, it is written, first written to the cache. Okay? First written to the cache. Then this data from the cache is copied to the cache on another node. There are 2 nodes, right? One I would contain 2 nodes. So data in this cache is written to the cache on another node. After that, an acknowledgement is sent to the host telling that data has been written, even though data is not flushed inside the disk drive where they are supposed to go. Right? Now think about a scenario where commercial power supply goes down and there is no battery backup available, right? In that condition, what will happen? Cache data will be lost. So we will end up in a situation where there is a data loss, there is a data unavailability, data loss scenario, and customer will definitely panic because of that. So in order to come out of that condition, we have the battery backup supply here. Purpose of this battery backup supply is to keep the storage running for a period of around 2 minutes. During that time, all the data in the cache is being staged or written inside these boot drives. Okay, it is striped across these 2 boot drives, whatever data is there in the cache, so that the data, whatever data is available in the cache, will stay with us. Okay, we are not going to lose the data. Now, when the power comes back on, data that is available in the cache is written back to the original drive. It is pumped inside the original drive. So that is the purpose of having battery backup supply. Okay.
So we have come to the end of presentation time today. I'm sorry that it took 5 minutes more than expected, but now we are going in for the question and answer session. Please shoot up your questions.
At any point of time, is the cache always